All right, so in this video, we are going to show how we can apply mathematics to chemistry in an example involving radioactive decay. So let's hop over to Delta Math and grab this question here. This is an exponential functions question, and it involves the decay of an element from one mass to another. Where at the end of it all, we're going to be asked to find the remaining amount, or the amount of time that it takes for the element to decay to a new amount. Okay? So what I need to do here is just grab this and throw it into my OneNote so we can work on it. We'll paste the question here. All right, let's take a look at this thing. An element with a mass of 360 grams decays by 14.7% per minute. To the nearest tenth of a minute, how long will it be until there are 20 grams of the element remaining? Okay, so the way that we teach this in mathematics is we introduce the students to the concept of the exponential function. Okay, which can be written in equation form as y equals ab to the x. Now, it's very important we identify what these letters actually mean. Y references some future value or some end value. A represents the initial or starting or present value. And b equals plus, or rather 1 plus or minus, depending on whether if it's decay or if it's growth, 1 plus or minus the rate as decimal. So the decimal version of the rate. We're usually given these rates in percents, and we have to convert to a decimal. So one of the things we want to look at here is, are we dealing with growth or decay? Well, they give us it right there. So the version of the b that we're going to use is b equals 1 minus the rate of decay as a decimal. Okay, and then the only unusual thing that this problem has is actually, it's going to be an easier problem because the half-life of the element is apparently equal to 1 minute. So there is we don't have to divide time by some other number. So we'll just be able to plug in our numbers to this. And we'll try to look at another example where there's a half-life. So what is the future value of the element? Let's try to fill in some of these numbers before we get started. So the future value is 20 grams. So over here under future value, we'll want to say this is going to be equal to 20 grams in the future. And the present value is 360 grams. Okay. Now I should say x, the x is the thing we don't know. And that is going to refer to time in minutes. Okay, so x is time in minutes. So now we can fill everything out. We still have to figure out exactly what b is. So we should probably do that first. So b equals 1 minus the rate as a decimal. So that would be 0.147. 1 minus 0.147. All right, that's my b value. So let's plug everything in and get started with the problem. So instead of y, I will write 20 equals, and then instead of a, I'll put 360, open parentheses, 1 minus 0.147, and then raised to the x. Now the very first thing I need to do, I'm trying to isolate x. So the very first thing I need to do is divide both sides by what we could call the coefficient of the b variable. So that would just be 360. I'm going to divide both sides by letter A, which in this example is 360. And we're not even going to try to reduce it, okay? We're going to let the calculator help us in the end. But that allows me to cancel those values out. And now, on the right side, all that remains is 1 minus 0.147 raised to the x. And then on the left side, I have 20 over 360. Okay? Now we have to use the power rule of natural logarithms to actually bring this x down. That's what I want. To get the x out of the exponent section, I have to use the power rule of natural logarithms. So I'm going to put both sides of the equation in parentheses and then take the natural log of both sides. Now the net effect of doing that is, on the left side I have ln 20 over 360. But on the right side, I now have x down in front times the ln of 1 minus 0.147. Now notice I'm not doing the subtraction because we're just keeping all values exact and we're not doing any work. We're going to let the calculator do all the work for us. So now my final step is just to get x by itself. I'll divide both sides by the ln of 1 minus 0.147. Okay, so over here I'll have ln of 1 minus 0.147. Okay, and then on the right, that cancels out. And I'm left with x equals, okay? And I just need to plug this into my calculator, which is what we're going to do right now, ladies and gentlemen. Let me pull up the calculator and hit second plus 712 to clear the memory. And we're just going to type this in just the way it looks. So all I've got is basically a fraction. So what I'm going to want to do here is hit alpha y equals, okay, and then enter. And that's going to allow me to create a fraction numerator over denominator. So I'll hit enter. And now you see I've got this fraction. Well, I'm going to plug in ln, which is the key to directly to the left of the 4. And then I'll have to hit alpha y equals enter again, because remember over here I had a fraction. And so I'll do 20 over 360. Okay, and then close that parentheses off. Down in the denominator, I've got the ln of 1 minus 0.147. So I'm going to hit ln of 1 minus 0.147. Close that off. This should look just like this, all right? And it does. So let's go ahead and hit enter. Now the answer, which we're going to pull right into OneNote, is given to us with a lot of decimal places. So the problem said to the nearest tenth of a minute. So what we'll do is we'll come over here and look at our answer, and we'll look at the tenths place, and then we tell the students, all right, look to the place directly to the right, and if that is 5 or greater, you need to round. So this little 1 needs to become a 2. So what we'll say here is x is approximately equal to 18.2 minutes. All right, so let's go back to Delta Math and see if that's right. 18.2. Here we go. 18.2. Submit answer. Let's see if we're right. And we're right. So that is how you do that problem. Okay, so now the question would be, I want a problem that has a decay rate with a half-life. And I think I might have just passed one. You can just keep renewing this. Nope. Maybe I have to go into the harder ones. Let's see. I think I might have to go into these harder problems. Huh. I mean, we were getting these before where it had a quantity decays exponentially. Where's the element with the half-life? Let me just go back and try to find it. Maybe that was from a more advanced one that we were doing. Kind of surprised I couldn't find that. Anyway, this is how we teach the kids to do it, and we'll leave it there. Actually, I really do want to find the one with the half-life. Let's see, where did I put that one? Solving Exponentials live stream. I bet that's in here. It is. Here's the problem. I don't know why it was so hard to find this. So this was one here. Here was the problem. And I think I'll show this one in a separate video. Okay, so that would be elemental decay with a half-life. And see, you have to use this little bit more advanced formula here, where the variable time is divided by the half-life. Where in that other problem, we didn't have to do that. I'll just set it up here. So element X decays radioactively with the half-life of 12 minutes. If there are 890 grams of element X, how long will it take to be 111? So if we have 111 at the end, that's equal to 890 multiplied by, okay, and it says that it decays, well, because there's a half-life, the decay rate is 50% per half-life period. Okay, and that period is 12 minutes. So we would say 0.5 raised to the value of t over 12. Okay, so basically, guys, what you would do now is you would divide both sides by 890. Cancel, cancel. And then you would take the ln of what was left. Okay, so that would be ln of that. And we would have the natural log of 111 over 890 equal to t over 12 times times the natural log of 0.5. Okay, so now you just divide both sides by the natural log of 0.5. And these cancel out here. And so t over 12 equals ln of 111 over 890 all over ln of 0.5. And we just have to multiply out the 12 to finish it off. So t is equal to this whole thing put in the calculator, which we'll do now. We're going to hit 12 times alpha y equals enter, and then we got to put in the ln of 111 over 890 on top. So ln of ln alpha y equals enter of 111 over 890 close parentheses, and then down on the bottom, it's ln of 0.5. Okay, so ln of 0.5. And then that goes to 36 minutes and 3, or, well, we'll figure it out. So it wants it rounded to the nearest tenth of a minute. So t is going to be approximately equal to, we'll say t is approximately equal to 36.0 minutes. Let's go plug that in and see if we were, oh, I don't have that one loaded up. Okay. Well, let's see if we were right. Let me go back to that problem. Solving exponentials live stream. Yep, there we go. It takes element x 36.0 minutes to decay from 890 to 111 grams. And so we thought it would be fun to go on the internet and find other elements, to find actual elements with actual half-lives and decay rates. And we worked out that uranium-238 would take 13.5 billion years to decay from 890 grams to 111 grams. We really don't know if we're right or not, but we did try our best to figure that out using Google. So, yep, that's the end of the video. And let's say I hope you found this useful, and I really think that chemistry teachers could use this in their classes if they don't already. Just teach that natural log power rule, and you'll be off and running. Good luck. Thank you.